Hello, here we are with the third part of the 2014 Oxford PAT. So this is the first lot of written questions in the physics section. Question 13, given the circuit below, all the resistors have the same value equal to R. What's the resistance between A and B? Now, I had someone asking me about this because I always go on about how quick and easy these questions are of what we're actually doing when we're adding these things up. Yeah, how can you make it quicker? So a lot of people are going to be used to this bit at the top of saying, well, if you've got two resistors in parallel, then you've got a half, and we've got a 3/2 here. But let's look at a slightly more interesting bit when we got this block here. So we know that we've got a 2 and a 1 and a 1 in terms of our resistance on each branch. So all we're actually doing with the resistor formula of when we're adding things up that are in parallel is we're reversing what we're used to doing with fractions. So normally with fractions, we get a common denominator and add up the numerators. Now we want a common numerator and add up the denominators. So what I mean by this is when we're adding these ones up, is saying, okay, so 2 is we've got 2/1, and then we've got two ones. So we've got a 1/1 and a 1/1. So we need to now get a common numerator because we're taking reciprocals of everything. So let's make those ones all 2/2. Now we add up when we're adding them, we're adding the denominators, not the numerators. So that'll become 2/5. And that is now our total for that. It just saves us having to do all the reciprocal rubbish all the time. It just takes, so much longer writing out all this reciprocal stuff when this is what we're doing. We're just writing fractions down upside down. So now we can add in a +1 there. So we've got 3/2 at the top. We've got 7/5 at the bottom for these two bits. So let's try doing the same thing. We need a common numerator. So let's change 3/2. Let's multiply it by 7 to get 21/14. For this 7/5, again, let's get a common numerator by making it 21/15, and then add them up where we're doing the reverse. So we add them up and we get 21/29 because we're now adding denominators rather than numerators. We haven't had to do any of this, oh yeah, reciprocal with this, reciprocal with that, and all the rest of it. We're just doing our standard fraction rules, but we just flipped numerators and denominators. So that's what makes these things so much quicker. Of course, you have to remember to put the R in at the end because these are all R resistors. They're not 1 ohm resistors. So 21/29R. Obviously, you want to set it out slightly nicer than that. But this is the way that I think is a much more sensible approach for these resistor networks. Right, masses on springs. Mass M is attached to spring S as sketched in A, right? So that's that one. If it oscillates for a period T, so we got that there. What would be the period of oscillation if we've got 2 in series or 2 in parallel? So, okay, we've got a potential issue here because not everyone is going to remember that period of oscillation of a spring is 2π√m/k. So say you couldn't remember that, we're going to need to actually work out what that is. So we've got our force is mass times acceleration thing. So our force, if we're doing F equals ma on this, we're doing our Newton's second law. So our force is kx, the spring constant, multiplied by the extension. And that is going to be minus ma because the acceleration is always in the opposite direction to the displacement on this. So if we got a positive x, we got a negative a. That is equal to minus m times the second derivative of the displacement with respect to time. So we need something. If we've got x double dot, as in our second differential or second derivative of x with respect to time, x double dot, is equal to minus k/mx. So we need something for x, which when we differentiate it twice is going to come back to itself, but with this factor of minus k/m on there. So if you have x, because we know that sine goes round in a circle, doesn't it? You go sine, you go to cos, and then you come back to minus sine. So that all seems great. So now if we have sine of the square root of k/m multiplied by t, because this factor here, this square root of the square root of k over m is going to come out twice when we differentiate it twice. So x dot is going to be the square root of k over m times cos of the square root of k over m times t, and then our x double dot is going to have the minus k over m times sine of the square root of k over mt. Right, so that we've been through before in our SHM videos, so there's nothing new on all of that. That is our minus k over mx. So we've now got this function here. This is our position function, position as a function of time. So how quickly is that returning to the same position? It's going to return to the same position every time t is equal to 2 pi the square root of m over k. Because every time that happens, if you put t being that value in there, then you get 2 pi, and we're back where we started, because sine is repeating every 2 pi. So that is where we can now say that is a capital T, and that is returning us to the same position. That is our period of oscillation. So yeah, it's quite easy to work it out. It's not ideal having to go through that in an exam, because you would have spent a couple of minutes figuring it out. So if you've done enough work on springs and SHM, then that will hopefully be in your mind as to what's going on. Yeah, especially as you can think of it, sometimes people remember the 2 pi root L over G. So if you're thinking, well, okay, that's our pendulum, what are we changing really here? What are the key features of a mass on a spring? Well, I'm not saying this is how you'd justify the derivation of this, but in terms of remembering it, if you've got that for a pendulum, well, we're taking a length away and we're putting a mass in, and we're taking away the gravity and we're putting in the spring constant. So it's got a pattern there. Anyway, let's get back to the question. So we've got this for our period here. Now, if we've got 2 in series, our spring constant will that's going to halve now. So our new spring constant is going to be k over 2 for this, because we're going to get twice the extension for the same force, and our k is force divided by extension. So if we got the same force and twice the extension, we've halved the spring constant. In this case, it's going to be the opposite, because we're going to get half the extension for the same force. So this is what we're going to have on this, and we can see that the period is inversely proportional to the square root of the spring constant. So in this case, t is going to multiply by the square root of 2, and here it is going to divide by the square root of 2. So yeah, that's just plugging in this new spring constant into here. So if you put k over 2 in there, the 2 is going to go up the top, we're going to square root it, and that's going to be our factor. Whereas here, the 2 is going to stay on the bottom, and we're going to divide by root 2. So that's good. What would be the period of the oscillations in case A? So going back to beginning case, on a planet with surface gravity 2g. Well, it's going to stay the same. It's still going to be t, because there's no g in this. There's no g in our period of oscillation formula. So no difference there. So yeah, that's an involved question. We've had a couple of involved questions. Well, I suppose the first one was quite straightforward with a resistor network, but it gave us something to think about with a new method. That one was quite involved. Right, now we've got an electric motor lifting a mass. Right, so that's just hanging on the bottom there. Is there anything in the question that isn't in the picture? They've given us the 230. Right, D is 5. Okay, so D equals 5 centimeters. Let's get that out. And the mass is 100 kilograms. Right, so it's not messing around there. That's 100 kilograms. Let's just get all this out of the way, because I am going to have to scroll down. So that's done that. U is 0.5 meters per second. Masses of the pulleys and the string can be neglected. So 0.5 meters per second. Right, so that's good. What is the electric current driving the motor? So the power is going to be the volts times the amps, volts times amps, which is going to be equal to how quickly this thing is being raised up. So what is the work we're doing here every second? We're doing mgh over t. So, well, we'll take t as being 1. So we've got, in 1 second, we've raised 100 kilograms. G we're using 10, and in 1 second, we've raised it through half a meter. So that's going to be multiplied by half and then divided by 1. So we've got that, which means that I is going to be equal to 500 divided by whatever our voltage was, so 230. So 50 divided by 23 amps. So that's the current bit, that's done. What is the angular velocity of the motor's winding reel? So the angular velocity, so let's call it omega, that is going to be equal to 2 pi times the number of rotations that we get per second. So that is going to be, how many rotations have we had every second? So we're going up 0.5 meters. We got the issue of the pulley though. Right, okay, let's not get, so the thing with a pulley that you always have to look at is how many strings have we got, because that's giving us our force multiplier on this. So we've got 3 strings. So, and if you want to go through this in more detail, look at my video on pulleys, if I've put it up yet. I think I have, but I can't be certain. So 3 strings means that we've got 3 times the force, but we're going to have a third times the distance on this. So if we've moved up 0.5 meters on the mass, then that means we must have done 1.5 meters of string or rope or whatever it is on the reel. So we've got 0.5 times 3. That's how far we've gone. We need to multiply that by 2 pi. But that 0.5 times 3, we need to divide by the circumference in order to say how many rotations we've done in 1 second. So the circumference is pi times d. So that is pi times 0.05. So just to be clear on all of this, we've got that's how much string has wound round the reel. That is the circumference of the reel. So that is going to be the number of rotations that we've done in 1 second. And then we multiply that by 2 pi to get the angular velocity. So that is what we got. The pi's cancel. That is going to give us 10 times 6, which is 60. So 60 radians per second. But yeah, you have to be careful with these pulley ones, because yeah, you're not just getting the same bit. You know, we pull in some rope here and you're pulling up a bit 3 times. So that's why you're getting that force multiplier, because we've got the same tension throughout the rope. We've got 3 times the amount of force. But if you've done 3 times the amount of force from our work energy principle, you have to go a third of the distance. So each one of these bits of string here is moving a third of the amount. The mass is moving up a third of the amount. So you have these multipliers. That's what's going on with pulleys. That's why they're so useful with simple machines. What is the force F with which the motor is pulling? Right, well, the motor is going to be going at we've got a force F here. We've got a 3 times multiplier on this. So we're lifting 1,000 newtons. So we've got 1,000 kilograms multiplied by the 10 for G, and we have to divide that by 3. That's our input force. That's our output force. So we've got that 3 times multiplier. That's what we've got there. Exactly the same reason I was just talking about with the pulleys. So if you pull with 1,000 over 3 and you've got 3 strings, that means you're then lifting the mass with 1,000, which is what we need, because that's what the weight is. So yeah, if you had a 4th string, then we could drop that down to a 4 at the bottom if you had 4 strings. You know, if we went back round again and then reattach at the top. So yeah, good stuff with pulleys. That's a complicated question because I'd imagine a lot of people wouldn't have looked at simple machines all that much, which means they're going to make mistakes. They're going to leave these factors of 3 out in the second and third part of the question. But simple machines is a wonderful area to look at in in mechanics all round. Really, it's fascinating stuff. Right, so where are we now then? We are on to diodes. Right, okay, right, another topic that people probably are going to be a little bit sketchy about. So we've got this setup of diodes. Sketch the current flowing between points C and D as a function of voltage applied between points C and D. Right, so we could have, well, voltage could go either way. Well, so can the current. So we've got diodes, well, it depends which way round as to which way they're going to run. So say we just add, sometimes a nice way of thinking about this is, what if we only have one of the diodes? Say we ignored the one on the right, then we're going to get current, we're only going to get current in one direction because that's what the diode is doing, and it's going to kick in when we get to our like threshold voltage V0. So we've got that if we were ignoring one of the diodes, but of course the other diode, it would be allowing current to go in the other direction if the voltage was reversed. So we're going to get the negative of that. That if we had an opposite voltage, i.e. we had a negative one, we'd get the current, the same current flowing in the other direction. So we'd have a minus V0 there, and we're going to get this symmetrical setup. And whether you want to put in a sort of, a very tiny, because you're going to get tiny current coming in on either side, but it's often, I don't think they mind if you leave that bit out. It's negligible, or you could just say that there's some negligible current, make a statement about the graph. Anyway, that's the first bit. We still seem to have a lot else happening here. A sensitive amplifier is connected to terminals E and F. Right, so we've connected something across here. Don't know what the symbol for an amplifier is. To measure small electric signals from an instrument connected across A and B. So we've connected something over there. Great. From time to time, there are discharges in the instrument that might destroy the amplifier, right, which is why we want it to go through the diodes. Explain how the diodes protect the amplifier. Right, so we got a split here between the small signal and the discharge. So if we got small signals, then that means we've got low voltage going on. So there's going to be negligible current through the diodes, negligible current between, what was it, C and D, between C and D. So, and we could say, yeah, the amplifier works fine. Amplifier works as normal. But then you've got the discharge thing, and you can see what's going on here. This is more or less saying that if we've got small signals, we're operating in this region of this graph that we've just drawn out. If we've got large signals, the discharge, then we're going to have high V, which means that we're going to have CD becomes low, well, it becomes low resistance. I mean, this is the other way of thinking about this. That maybe the interesting part of these IV graphs for diodes is how the resistance is changing. We're saying we've got high resistance here, and it's ever decreasing as we go up here. So C to D becomes low resistance, which allows current flow, and that protects the amplifier because we're getting now a low resistance path between C and D. Whereas for the small signals, the low resistance path is between E and F. So you might want to put it that way round as well. So E to F is the low resistance path, whereas here we've now got the amplifier is protected. Amplifier protected because it's the high resistance path. So this is really what we're trying to do with these diodes. We're trying to flip the resistance around, which is going to be the path that the current is mostly going to be following. So if you're thinking of this from a sort of electrical engineering point of view, that's what we're messing around with diodes. how can we have something which is going to be responsive to voltage to change resistance to influence current? So it's like changing a flow in a river. You can have various blockages. If you've got some path through a river which has got a channel which is blocked up to a certain point, so we've got very high resistance here until the voltage, the flow in the river, say the height of the river reaches a certain level. When it reaches a certain level, all of a sudden this resistance is overcome, and now this becomes the channel that we're moving down, not this one. It's changing, it's flipping that around, trying to get that in your mind of what we're manipulating. If you're trying to build a circuit, I don't think this graph paints a picture of what it is we're trying to do when we're putting the components together in a circuit. We're trying to manipulate resistance to change current flow based on voltage, based on energy differences. Because remember, voltage is all about energy differences. So if you're starting to get concentrations of energy in one part that needs to be released, which is the discharge. So a discharge is a release of energy. That is going to mean we've got a high voltage. And you want that to go in the right place. It's dangerous to have a lot of energy going down a path that you don't want it going down. So you want a circuit that can respond to that. You want a circuit that can change its resistance based on where the energy is. So that's why these diodes are such good safety mechanisms. You get a build-up of energy and they respond. They have a different resistance that allows that energy to be safely removed. So that's how we want to be thinking about circuits, not just these faceless graphs that are kicking around. Anyway, I got a little bit off topic there. Well, on topic, but off question. If you're just coming here for the answer, then maybe you didn't want to lecture on circuit design. But you never know, maybe you find it interesting. Question 17. For this question, you may assume that the electrostatic potential energy of two positively charged particles separated by distance x is given by that. Okay. Two charged particles are placed, distance d. One has that mass and charge, the other's got that mass and charge. Charges are initially held stationary, then released. Find an expression for the maximum speed of the heavier particle. Okay, so they're going to repel each other. We're going to do conservation of momentum and conservation of energy. This is usually what we've got on all of this. So conservation of momentum, we start with nothing, and it's going to go to, we're going to have an mv1 and a 2mv2. And we want to find the maximum of mv2. They're going to split the velocities differently because we've got different masses. So we can say v1 is equal to, oh no, these are in opposite directions. What am I doing? So that's going to be a minus because, yeah, they're repelling each other. And we can say that 0 is equal to those. So v1 is going to be equal to 2v2. So the lighter particle is going to move away faster than the heavier particle. So we've now got conservation of energy. So we can say that a half mv1 squared plus a half of 2mv2 squared, so our two lots of kinetic energy, is going to be equal to our initial, this is our electrostatic potential energy we've got to go with. So we've got a K, then we're going to have Q times 2Q, so 2Q squared. And our X was, what did I say? D. So we've got that. We know now that V1, let's scroll down a bit, is we can sub out the V1 because we want to find V2 on all of this. So that's going to be, what have we got? So we got V1 squared. So it's going to be 2mv2 squared plus mv2 squared. Okay, so that's 3mv2 squared is 2kq squared over d. So that means we've got v2 squared is going to be 2/3. Well, we got a k, a q squared, and an m and a d. Right, so v2 is just the square root of all of that. Oh, we can bring the q out. Not that that's really adding huge amounts, 2K over 3MD. Right, so that was fine. I think they're just trying to scare people off with this, with the amount of what looks like new stuff in the question. It's quite a lot of words. We might not be familiar with this equation. So, yeah, but otherwise, there's not a lot to say about that one. Oh, and now we're on to the long question. So, yeah, I've probably taken quite a while to go through those because I was having a bit of a rant about, well, not a rant, but an explanation about circuit design and also how to think about resistors and adding those up. They were 3 or 4, I don't know, I can't remember how many it was now, but however many questions they were nice questions. I like that section. I think they were very well pitched. So, yeah, pleasing bunch.